Welcome back. We're continuing with digital signatures. Last time we looked at the definition, syntax, and the UFCMA security notion, and we studied how to achieve digital signatures based on RSA in quite nice and simple ways. Now, when we studied number theory, we saw that its purpose, in one way at least, was to give us hard computational problems which we can rely on for security. And we had two main examples. One was RSA, but we had started with discrete logs, the problem of taking a discrete log in an appropriate group being computationally hard for an adversary. And we had shown how you can get public key encryption based on the computational Diffie-Hellman relative of the discrete log problem. So we now ask the analogous question for signatures. We've seen how to get it from RSA, but how do we get signatures from discrete logs and in cyclic groups? And it isn't a mere curiosity. Nowadays, in fact, digital signatures based on this approach are dominating because when you use elliptic curves, they end up being a lot more efficient than RSA. Okay, so let's look at an example scheme, and this is the Elgamal signature scheme. You have to recall all our discrete log-based math. So we'll let the group be the integers mod p relatively prime to p. Remember, that's the numbers from 1 through p minus 1, and the group has size p minus 1. Let G be a generator of that group. And as with most discrete log-based systems, the public key is a group element of the form G to the little x, where little x is the secret key, and that secret key was a random exponent. So it's drawn at random from this, which is the space of all possible exponents. Now coming to the scheme, we've seen lots of schemes in this class, but this has got to be one of the weirder ones. So it does stuff that's fairly unintuitive. So how do we start thinking about it? Let's first look at the verification algorithm. Remember, as a digital signature scheme, you have to have both a signing and verification algorithm. Verification takes the public key big X, a message M, and a candidate's signature, and is supposed to return 1 if the signature is valid and 0 otherwise. As we see from this, the signature is a pair. It has two parts, R and S. What the verification algorithm first does is if R is not a group element or S is not a valid exponent, it rejects. That tells us it better be the case that this is a group element and this is an exponent. And having gotten that out of the way, here's the main step, is that a correct signature R and S must satisfy this equation. This equation says take the public key X and raise it to the power R. That's possible because R is an integer. Then take R and raise it to the power S, multiply those, and see if you get back the same as raising the group generator G to the power of the message. All of this in the group ZP star, hence the mod P over here. What's weird about this is that R is a group element, according to this. And we don't usually imagine raising things to power as a group element. It works here because R is in fact just an integer. The group is ZP star. So its elements are integers, so you can raise things to integer powers. But here is treated as an exponent and here as a group element. And this fact of the R appearing in these two places in these two ways is kind of the weird part about this scheme. But in any case, that's the verification, and we'll now look at signing. Now, even given this, it's not necessarily clear how, given a message, I'm going to generate a pair RS satisfying this equation. It turns out that we do it through randomization. So the signer given secret key little x starts by picking a random point k. This will be an exponent, and it'll be drawn from this space over here. It then raises G to the power k mod P to get R. So that's our first signature component, which is a group element. Now it needs to find the second. So effectively, it's going to try to solve this equation for S. And it turns out the solution is like this. You take the message, you subtract the secret key times R. R is here treated as an exponent. It's an integer, so you can treat it either way. How do you know we're treating all this in the exponent space? Because it's mod p minus 1. Notice this is mod p, this is mod p minus 1. And here we multiply by the inverse of k. So what is that? It's the modular inverse of k mod p minus 1. We now see why there's a star here. That is because it ensures that k has an inverse mod p minus 1. Not every point mod p minus 1 has an inverse. In fact, for example, all the even numbers do not. So k will be something that does, and then you can do this step. Okay, but that's just a scheme description. What can we say about its properties? The first thing to check is correctness. We want to check that if you generate signatures like this, they do pass verification. So that is just algebra. So first off, it's clear that this part is okay because this R is a group element and the S, since it's generated mod P minus 1, is in ZP minus 1. So we look at the equation. We are assuming here that this has been generated through the signing algorithm, so all of these equations are true. And now compute x to the power r times r to the power s. And just substitute. Big X, here is the public key, is g to the little x. We know that from here. Little r from here is g to the k. So raising it to the s, we get this. Simplify that as g to the xr plus kx. And now substitute the value of s from this equation. So you get k times m minus xr times k inverse. The k and the k inverse cancel each other. Remember that in the exponents we work mod p minus 1 because in the exponent space everything is modulo the group order. So when this is gone, you get xr plus m minus xr, which is g to the m. And that means verification succeeds because that's what we had to get. So it's worth checking that you see how all that evolves, that you understand the difference between p and p minus 1, where one is used versus the other, and so forth. So now we have a scheme that's correct. What's the next question? Obviously, is it secure? And there, well, our understanding could be something like this. So here I've just read it in the scheme, is what is an adversary trying to do? Well, it has the public key big X. And let's say it has a message M and it wants to compute a signature, but it doesn't have the secret key little x, so it can't do this. It has to find some other way. It has to find an R and S such that this equation is true. How could it get such an R and S? Well, here's one strategy. Why don't I pick R in any way I want? I could even set it to 1 or pick it at random. And then I try to solve for S. But what does that mean? If I try to solve this for S, you see that S is the discrete log in base R, because this is R to the S of this quantity over here. But our adversary can't compute discrete logs. That's a hard problem. So it says maybe I'll try something else. Maybe I'll first pick S in some way and try to solve for R. But then you run into the difficulty that R is in two places, one up here, one down here. It's not clear how you even start writing equations to solve for it. So all that looks pretty good from the point of view of security. This is looking like, well, our adversary is going to have a seriously hard time violating security. But again, what makes it turns out that this is false, and what makes it so is to remember that our goal is UFCMA. And this is not the setup for UFCMA. The big difference is that in UFCMA, your adversary picks the message. It doesn't start by thinking someone hands me a message and I have to do all this. Once you allow the adversary to pick the message, things get very different. And here's what it can do. So this is a UFCMA adversary written out formally. Remember, its input is the output of the initialize procedure and is the public key. Now, it first starts by creating the R component of the signature, which is created by multiplying the generator by big X mod P. Remember, the generator is public. It then takes the second component of the signature to be the negative of R, and this is done in the exponent space. This is mod P minus 1. Finally, it sets the message to also be this value S. And so that's the triplet outputs. Okay, this is weird stuff, but all we have to do is see, did it succeed? This adversary made 0 calls to its signing oracle. It didn't even need that. It's saying I have such a strong attack that without seeing any signatures, I'll simply output a correct forgery. And we can go through the algebra. What is the algebra? It says, look at that equation, that x to the r to the s to g equal g to the m. Is it true? So plug in all the quantities. R is g times x. So plug that in here. Then you get x to the power r plus s, g to the power s. Now, s is the same as m. So you can write that g to the s as g to the m. And remember that exponents here will be modulo the group order. So you may as well put a mod p minus 1 here. It wouldn't make any difference whether you did or you didn't. But you see that if s is negative r mod p minus 1, this is just 0. And so this just goes away, x to the 0 is 1, and you get g to the m. So we have a valid forgery. Okay, so it seems like a weirdly roundabout way to get nowhere, because we developed this quite complex scheme, and now we're saying it doesn't even work. But as we saw with RSA, the fix is quite simple. It just says, when in doubt, you hash. So what we're going to do is we will use Elgamal, but rather than running the algebra on the message, we will first hash the message. The setup is identical to before. We have our cyclic group, P is a public prime, G is a public generator. The keys like before, big X is the public key, little x, the exponent here is the secret key, etc. But now we have a hash function, and we assume its output space is the exponent space, CP minus 1. So when I get a message to sign, having the secret key, I first hash it to get little m. And then I just do whatever I did before with little m, and that's the signature. So here you simply see the prior algorithm. How do you verify? Well, you have a public key, a candidate message, and the signature looks just as before. It's a pair. The hash function is public. You hash the message to get this quantity here, and then you just run verification of the prior scheme. And we don't have to revisit how that works. Okay, if you now assess security, you'll see that the types of attacks we saw earlier don't seem to work. They relied very much on the adversary's ability to pick the message, but if the message has to be the hash of something, it really can't quite pick that. By the message, I mean this value, right? It has the ability in UFCMA to pick big M, but if the hash function is good, it has very little control over little m. Of course, the requirement of collision resistance doesn't go away. So no matter what sort of signature scheme you have of this type, that you're simply hashing the message and then doing some other kind of stuff, you will need the collision resistance. So that requirement will be there. And there's also some other not so well partially understood requirements to prevent prior attacks. But the practical understanding is if you use a good well-derived hash function of the types we mentioned before, built from SHA-256 or 512 in a good way, then this works. So if you want good security, you have to use quite a large prime with the Elgamal scheme. There was a digital signature algorithm developed by the government which had the same type of arithmetic and algebra as Elgamal, but it made a few changes which resulted in greater efficiency. So in particular, while for a 1024-bit prime, signing and verification Elgamal were of these types of costs. This says you have to do a group exponentiation, which is cubic time, if the exponent is this length. More generally, exponentiation is an operation that here will take time, the length of the modulus squared multiplied by the bit length of the exponent. So those were the costs here, and this was the signature size. In DSA, they shrank things down so that the exponentiation used a small exponent, and that gave a significant speed increase. Right? So that's explained over here. And this is a Federal Institute of Processing standard. Now, we don't necessarily have to describe how DSA looks, but I thought I'd post a slide about it. One reason for this being that many years back, someone who took my class at the time, I didn't show them what DSA was like. And he later interviewed at Qualcomm, and one of their questions on the interview was, how does DSA work? And then he came back to me and said, look, I couldn't answer that because you didn't have it. So now I put it on the slide. But I'd like to remark that this person is now a manager of the security group at Qualcomm. So he got in and did quite well. So the change from Elgamal is that there will, in addition to the prime P, there's another prime Q, which divides P minus 1 and is quite a bit smaller than P. Now, our group G, if we set to ZP star, we used to call G the generator of this group. I'll now let H be a generator of this group and set G to be H to the power P minus 1 divided by Q, right? Since Q divides P minus 1, this makes sense as an integer. Always remember why these P minus 1s, it's the group order. We're always playing around with that. The result is that G has order Q. What does that mean? If I raise G to the Qth power, I get back 1, right? That's pretty evident because G to the Q is H to the P minus 1 and H to the P minus 1 is 1. By our usual result, then anything to the group order is 1. Our hash function now maps only down to integers in ZQ. So in particular, the hash results are much smaller. And then you have keys which are kind of like before, G to the X, the public key, but the secret key is drawn from this smaller space. And then you see very similar operations. You do hash the message, of course. You pick something at random, but from this smaller space, and then you have very similar equations. But notice you have a mod P and then a mod Q, and this is mod Q. And doing things mod Q is where all the cost savings come in because Q is smaller than P. The verification is written a little bit differently. The equation is a little bit changed. It also has mod P's and mod Q's. Okay, this is not the only signature scheme based on discrete logs out there. Nowadays, the elliptic curve versions are much preferred because elliptic curves are give you a higher security for the same size as we saw earlier. So things will be faster for the same security level. There are other interesting elements maybe worth noting about these schemes. One is that if you're doing a lot of signing, you can do expensive parts of it offline before you even know the message. When it comes to security, there's actually no proof that these schemes are UFCMA, even if you assume ideal hash functions. But in practice, this seemed to work fine. There is another discrete log-based method for signing, which is very popular and well known. It's called the Schnorr scheme. And it's about as efficient as the ECDSA, and it does have a proof. And we could look one place where that scheme arises. This is ED25519, is a very widely deployed signature scheme based on the Schnorr signature scheme. And this web page describes it and its various computers. You can find software for it. You can find running times and all that. So this is a good reflection of how signing is actually done. Here's an exercise for discrete log-based signatures where you are given some kind of scheme, and as usual you have to try to find some adversary violating UFCMA. This is a remark that arises due to the fact that when we studied encryption, we saw that encryption needed to be randomized to achieve our desired security metric of IND-CPA. If it wasn't randomized, it wouldn't achieve it. For digital signatures, it turns out randomization is optional. You don't require it or need it to get UFCMA, but it seems that some schemes use it and they find it helpful. So there is a bunch of randomized digital signature schemes. However, in practice, people have tended to implement deterministic versions of them because randomization itself introduces potential security weaknesses. You can see here, for example, standard on the deterministic usage of the DSA and the ECDSA schemes. Effectively tells you how to de-randomize them. Okay, finally, this is just some sort of curiosity I noticed, I thought maybe might be interesting. Here's someone on Stack Exchange talking about, are there digital signatures for which given two documents signed by the same key, one could derive the key? And he claims, or he or she claims, that this was interesting towards the design of a cryptocurrency. And people have answered the question and so forth. And I think it's actually a fun problem. Go ahead and design such a scheme, and there's many interesting ways to do it.